primarily and basic knowledge of a PN junction. Now, if you are being electronic students or if you have studies in electronics in class 11th and 12th, we know basically that diode is a one-way current flowing device which are used in primarily all the electronic systems, and now also as a controllers in electrical system also for the controlling function. Now here we will take basically the physics of a PN junction as to how it works, how it supports, and its basic information. So, so to proceed with our lecture, we are, as you can clearly see, we have jotted down the outlines as to how this lecture will flow. Now here, we can see that the primary first point is the concept of energy band for basic P and N types, then basic structure of a PN junction. And so moving on, some advanced topics related to the energy bands, and finally the current voltage characteristics, which is of a practical relevance to run an electronic system. Now, PN junction, and primarily we will talk about PN junctions in using some keywords such as energy bands and energy gaps. Is basic information, and then we will combine with this junction value. Now, since we all know that electronic states in solids are grouped into energy bands, these energy bands internally, basically means in the physics, are separated by energy gaps, in which no electron or charge carrier can exist. Now, in a semiconductor at low temperature, all electrons are confined to the valence band, which is full, having its bonds with the nearby atoms, so that no free carriers are available for conduction. Low temperature means a temperature little below room temperature, or on the verge of a room temperature. In the conduction bands, basically electrons can exist there only if there are free charge carriers available, else there will be no free electrons. So whenever electrons has to move within a confined atom or crystal lattice, it can use conduction band only and only. And after conduction, it has to return to the valence band. Now, electrons in bands are either completely empty or completely full. So, in this condition, it cannot contribute to conduction. So, primarily, semiconductor at low temperature cannot conduct. Now, as far as we have discussed here, we are basically talking about the intrinsic or pure semiconductors, in which there may be no dopant or external impurity added. Now, keeping it in pure or intrinsic form, if temperatures are risen, then due to the external energy provided to the crystal lattice in the form of temperature, some bonds can randomly break, and in this process, a bond which is broken between two nearby atoms, it can be random, will create an electron and hole in pairs. As you can clearly see in the diagram, that as we have already mentioned clearly, the electrons in its natural states exist only in the valence band. So as soon as external energy is provided to them, the electron jumps to its high energy state, which is primarily a conduction band. Now, this jumping is made possibly only if energy was sufficient so that the forbidden gap, which is shown here by the EG, is clearly overcome. Otherwise, electron wouldn't go to the conduction band for the conduction. Now, since these carriers are not due to the impurity atoms, like in extrinsic PN junction, so they are always in pair, and they contribute a little bit of conductivity, but this conductivity is of not useful value and can only damage the physical device. Now we come to the basic two types of solid state systems in which two impurities are being created, P and N type. Now we can clearly see in N type of doping, the pentavalent impurity atoms are used as a dopant. So these create excess of electrons, and these excess of electrons work as a carrier, and carry electrons can only exist in the conduction band. So in the first diagram, which is mentioned in the N type, excess electrons are available only in the conduction band, and few holes are available in the valence band. Now, as we move to the right hand side, the doping impurity is of nature trivalent, which creates excess and of holes carriers. And holes are actually vacant space. They don't have mass. So they cannot exist in the conduction band for conduction, as they have charge equal to electron but no mass. So it is a hollow space and it can only exist in the valence band. So as for now, we are clear that if excess free electrons as carriers are available, they can and they will exist in the conduction band. And if holes are available, they can only exist in the valence band. Now we move to the region of interest, which is basically a PN junction diode, which is the primarily or a specific component in most of the electronic devices. Now here, substrate is taken in the form of P-type material, and N-type materials are sprinkled in the form of fine particles, and this whole system is made to put in some type of oven, so they can fuse and diffuse internally to the atomic level. Now, P-type, basically, we use an example of a boron, and in N-type region, we basically use example of phosphorus. It could be anything, any element which has trivalent and pentavalent impurity. Now, here we have taken a detailed diagram of PN junction. Now, a PN junction diode is shown here in the condition of no bias, which means no external energy source is applied here, and the width region is generally called a space charge region. Now look at the basic labelings here, which is shown in the blue color. From beginning from top to bottom, Na is a negative charge and Nd is a positive charge. Na and Nd are basically the doping densities of atoms which are used as an impurity. Since on the P side, acceptor impurities are there, which accepts electrons. So any atom which takes electrons takes on to the negative charge. And to the right-hand side in the injection, basically this is the donor. And whenever an atom gives an electrons, it takes on the positive ion charge. Now due to this positive and negative space created, it has risen to the electric field, which we already know that it moves from plus to negative sides. Now, throughout the diode, the basic primarily mode of conduction is diffusion. It is a very important consideration. that electrons and holes move through the process of diffusion inside the conductor. Now, as is shown around the dotted arrows, the electric field created due to the diffusion region forms doesn't allow the field to move towards the junction, and also this same field does not allow to move electron from the n region towards the junction. So once after manufacturing, a junction diode depletion region is formed. So unless and until an external field is applied in the positive direction, there will be no charge carriers present inside this space charge region. Now, no bias condition is basically a reference which is shown in the PN junction at equilibrium. Now, as we have earlier seen, that due to this creation of electric field, whatever charge due to their doping concentration or charge concentration were moving, once a space charge region or depletion width is formed, this movement totally stops. Now, how much is the width and how much depth of penetration that both charge carriers can move inside inside the opposite sides, which means how deep can holes move in the end region for the formation of depletion width, and how far electron can move inside a p region. Now, they are very primary factors as we jotted down here one by one: density gradient diffusion, accumulation of excess charges, the electric field formed inside the depletion width, and all the resultant of this combination, this whole thing works. Now, a more elaborate diagram is here in the show. This diagram is just before the formation of depletion width after diode is manufactured. So we can clearly see from the top, H plus is the holes. So the process of diffusion moves towards its less concentration, and the same way electron from the n type tries to move towards their less concentration region. And since holes and electrons have the same charge, they annihilate each other in the absence of any external field, and slowly depletion width is created. Now, as we show in the bottom labeling, there are two movement forces mentioned: hole diffusion, hole drift, and electron diffusion and electron drift. Now, these different forces need to be considered with great detail here. Now, at the manufacturing, it is intentionally made. The doping concentration is a little more on the P side, and doping concentration is a little less than N side. Basically, this is the manufacturing trait, and this is primarily done. So since the holes have a less diffusion speed, so in order to counterbalance them, their quantity has to be increased to create that impact which electron creates, since it has mass and moves faster than holes. Now, energy band diagram is given in this current slide, which clearly shows. Now, some interesting things are mentioned here. P and N type, there is a dark line drawn, and built-in voltage is shown as V0. This is primarily the knee voltage, which we deals in the no bias condition, and it shows the hindrance or problem available Now, a detailed diagram is shown in the bottom one, where there is a conduction energy level is shown moving from P to N side, and a valence band system is shown from moving from P to N side. Since Na is greater than Nd, so the conduction and valence band level are a little high than the N side. And if we consideration, see the dotted line, it is an extrinsic Fermi level, which on the N side remains close to N type, and on the P side remains close to P type. And there is also another level which is known as intrinsic, just moves midway between EC and E. Now, there are basically two regions which we need to consider: forward and reverse bias. And now in the tabular form, this is shown where V is applied as the external field. Now what this field does in forward and reverse bias. In the forward bias, the depletion region shifts slightly inward because the electric field present in this space charge region, its electric field is far much less than the energy field externally applied. So the external applied field forces the electrons and holes to move across the junction, which actually creates the resultant current. Now only electrons leaves junction diode as it has only mass, but holes cannot leave inside the PN-junction diodes. That's why it needs to be remain electrically neutral. Now in the previous diagram, there is a built-in voltage shows V naught. This is the condition basically in the no bias condition. Means nor forward is there, nor reverse is there. As soon as forward and reverse biasing is applied, as we know from our earlier concepts, that in the reverse biasing, depletion width increases. In the forward biasing, depletion width reduces. Now this reduction needs to be dealt with in the form of energy bands. So in this very elaborate system is given in which no bias and forward bias condition is mentioned. So two movements are happening here as electrons and holes due to the diffusion moves from their opposite regions as shown by the broader arrow here, and H plus and E minus. And intentionally the external applied field forces the holes and electrons, since they are having the same charges, to also cross the region. So if we look in the right hand side, what this forward biasing done is shown by VF. Forward biasing is shown by VF, and V naught is the voltage in the no bias condition. So earlier it was only V naught, but as soon as VF is applied and it keeps on increasing, the resultant value becomes V naught minus VF. So we can clearly see the earlier barrier was V naught, and now it is less by the amount VF. So by how much amount the VF rises, the resultant V naught VF decreases, and the height or barrier to cross the carriers from either side is reduced, which eases the transfer process to diffusion. Now the electric field is given. Now some interesting parameters are there. Dead drift does not cancel diffusion, and depletion region becomes smaller, potential barrier becomes smaller. As soon as VF keeps on increasing, large forward current can be seen. Now extrinsic Fermi level is shown by both the sides from EFN and EFP. In the earlier diagrams, as we can clearly see in the earlier diagrams, in the bottom, we can show here EF is moving exactly midway, and it is closer to the N side, and here it is closer to the P side. But as soon as forward biasing is given, it becomes a little distorted since EC from N type material has moved upward. So EFN always move towards the electron, where electron concentration is greater. So there is a breaking, And this energy breaking is governed by the external energy which is supplied by the battery, which is given by Q into Vf, as work done or energy is given by Q into V. Same thing goes on reverse bias. Now another reverse bias diagram is given, and this reverse biasing keeps on adding. Forward biasing keeps on subtracting from V naught. The reverse biasing keeps on adding. So as you can clearly see, the reverse biasing carriers feel much more hindrance in moving to their opposite regions. Reason is clearly shown here. The EC region from inside has moved more downwards, which creates this wall region high, which is shown in the form of Q V naught plus EF. So electron and holes face a larger energy level, which flows or blocks their movement from their high concentration to low concentration regions. Now, various electric field and values are mentioned here, that diffusion does not cancel drift. Earlier it was also same. Depletion region becomes larger and potential barrier becomes weak. And a small reverse current, which we already know that the reverse current is in the value of microamperes, and it's more dependent upon temperature rather than the energy source of light. So if we keep on increasing the reverse voltage and temperature is maintained, so if we avoid the breakdown region, current can be only in the very small amount in the form of microamperes. Now, comparison diagram is shown here, in which the first figure is of a no bias condition, and we can clearly see EFN and EFP on the same level, and energy difference is shown by the built-in barrier potential VBI. Now, as soon as reverse biasing is applied, this region increases, and EFN move more below to the valence band level, which is shown by VBI plus VR. And in the rightmost diagram, it is shown in the forward bias region, and energy level decreases by the amount VF, and EFN and EFN then also to redistribute themselves as shown in the diagram. Now, all this physics involved and energy bands and quantum states are governed here. So all this results in the current voltage relationship, because basically we have to channelize current in a particular direction using diode and create various applications. So the IV characteristics basically governs in the three regions: an earlier stage where there's very less or negligible amount of current, and then a region where the current slowly starts increasing. And as soon as we move towards the break-in potential value VBI, or primarily the knee voltage, as soon as we crosses the knee voltage, current is shown as an exponential rise. Now, all this which I have mentioned here is shown in this particular graph. You can clearly see the region from A and B, in which the current is very less than the knee voltage, and forward bias voltage is very much less than the knee voltage from A to B, and current is showed minute increase. Then from B to knee voltage point, there is a slightly more increase in current, and as soon as knee voltage point is crossed, from knee to C, an exponential or sudden rise in current is observed, which means depletion width is primarily must very much reduced to a very negligible amount in the range of 0.001 microamperes. And this exponential or huge amount of current increase can only be limited by external current. So we have to be careful by designing a circuit so as to how the minimum load and safety loads has to be put, so that diode does not burn. Now the same IV characteristics is shown in the reverse bias region. We can clearly see the current is of a much constant value till the breakdown region and very negligible amount of current due to minority charge carriers. But we have to always see the data sheets as to whatever is the breakdown region, and accordingly the battery system or maximum applied voltage system has to be used mainly by considering the breakdown region, because in forward bias we can limit current by adding a external source. But if a reverse breakdown region is not being considered and whatever applications we are creating has a large value, then it could result in the destruction of diode device. Now, this is the basic diode equation. We all know I equal to Is exponential V by Vt minus 1, where it is the basically thermal voltage, and at room temperature it is approximately 25 to 26 millivolt. This mathematical equations can be also used for forward and reverse bias current value. For example, in an approximate way, when V is a positive nature, since Vt if considered at room temperatures always will be the constant. So if Vp is positive and 0.7 to 0.6 volt, then exponential value will be much larger than 1 and it could be ignored. So the current in forward direction is given by the exponential nature, which is clearly shown in the graph, which is mentioned here in the right hand side. And if in the reverse bias V is negative, so exponential term will become much less than 1. So it can be ignored. So I becomes minus Is, which is shown in the reverse current. Minus signs shown that if forward current is the plus Y direction, then reverse is in minus Y direction. And since I equals to minus N, Is is the saturation in nature. So Is basically remains as a constant value. So if we revise and correlate various things in the forward and reverse junction, see this clearly diagram. Since extensive Fermi levels always remain close to the where the charge gauges are maximum. So in n side electrons in the conduction band, so EFN remains closer to the EC in the n side, and EFP same remains close to the valence band side. So in the reverse and positive, what happens is we take EFP as a reference, and since EC moves upwards, so extrinsic has to be remain to the closer to the conduction band in the n side. So EFP moves upwards. In the reverse bias, when EC moves downwards due to the more non-availability of electrons, so its energy states become less and it goes way beyond the valence band level from the n side. So we can clearly see the increase in height from the no bias condition and decrease in height in the forward bias from no bias condition, which becomes primarily the exponential rise value. So students, this is the basically forward and reverse biasing in the applications of energy bands. So in the next more advanced lectures, we will see the probability equations and availability of electrons, so as to go more specific for the current voltage characteristics. Thank you students for now. Have a good day.